Come on now. Come on, yeah! Here we go. All right. So we have an isolated log. So mission accomplished. Normally that takes a little bit of work to do, but right now we have an isolated logarithm. After you have the log isolated, write it in exponential form. So translate this into its exponential form. In order to do that, it might make sense to write this like that, because when you translate a log into exponential form, we say, okay, it's this raised to this power, and that value is equal to 2x. That's all for x. What are we going to do? Divide by 2. If you're looking at that and you're saying, well, shouldn't I figure out what that is? That's a number that's close to 3 raised to the 12th power, right? You're going to get a scientific notation answer in your calculator. That's a pretty massive amount, right? So most people are going to tell you this is a totally acceptable answer. But like I said, we have to. When we get our solution to a logarithmic equation, we have to make sure that its value is substitutable. I think I made that word. I think I just made up that word, okay? I have to make sure that that value is substitutable back into the original statement, because this has to be positive. So even though in the solving process may all be legit and totally correct, right? When I get to the bottom, if this ended up being negative, now it isn't, right? It's a very big positive number. But if this ended up being negative, if I plugged a negative number in here, this would be negative, and I would have to say that there's no solution, right? You cannot take logarithms of negative numbers. That's the bottom line. So when you solve, you got to check it. You got to check it, okay? Let's do this one real quick, real quick. Camera's rolling. Camera's rolling. All right, camera's rolling. We've said you want to solve a logarithmic equation, isolate the logarithm. You're like, oh, I don't know, there's 2. Well, isolation doesn't mean, elimination is not implied in isolation, right? Isolation just means get it by itself, a singular log. That's why we have those condensing properties. This is the difference of 2 logs. So I'm going to be able to condense this in order to create one logarithm on the left side of this equation. So I've got log base 2 of x minus log base 2, so the difference of 2 logs is the log of their quotient, and that is equal to 3. So I have isolated the logarithm. The constant's on the other side. Once the logarithms have been isolated, write it in exponential form, which is 2 to the 3rd power equals x over x minus 7. This is a rational equation. 2 cubed is 8. 8 is equal to x over x minus 7. Now, I don't know how comfortable you are with solving rationals. People kind of have their own way of doing it, right? Here's how I'm going to do it. I've got a ratio and a whole number. Sometimes the old switcheroo works, where I just take these and swap them out. But if I did that, I'd still have an x in this fraction. That wouldn't quite work well. Some people multiply by the fraction on both sides to clear it out completely. Now there's no more fraction. That works. So you can take this and multiply by x minus 7. You'd have to multiply this side by x minus 7. The x minus 7's cancel. So I have 8 times x minus 7 equals x. Should we just go with that? We can just go with that.
Yeah.
I was going to set up the proportion. I was going to call that 8 over 1, and then I was going to cross multiply. That's what I was going to do, but same result. Multiply by x, or excuse me, by 8, distribute, subtract 8x to the other side, divided by -7. Presto changeo, x equals 8. Now, any questions? Did I make any mistakes? I think I'm good. Make sure it works. Can I put an 8 here? Yes. Can I put an 8 here? I better check. 8 minus 7 is 1. Okay. Right? But if I had went through this entire process and got 6, that would be no good, because I can't put a 6 here. Let's do this one.